Yes.
Yeah, okay, fine. Okay, so my name is Christophe Peyrad. I'm part of EDF R&D. And as said Martin just before, I'm going to present you some insight of the work that was done within the Hiperwind project on the wave loads applied to monopiles. So I didn't know that Martin will give you the context, so I prepared a slide about the Hiperwind project organization. I don't know if you see it. Seems to be a bit. Yes, okay, fine. There is a lag, but that's fine. So within Hiperwind, there are of course a lot of work packages. The global idea of the project is to quantify the uncertainty that we can have in the offshore wind design, both for bottom fixed and for floating. And as you see, we are going to talk about a very central deliverables in the work package 3.2 on the aero servo hydroelastic model uncertainty. So of course it's a small part of the work that was done, but we'll try to give you the most important results that we have for the monopiles and for the floaters. So on my side, I'm going to talk about several components of the uncertainty we can have on the wave loads applied on monopiles. So my global idea is to focus on the DEL, so the damage equivalent load, rather than the ultimate load. So all the study will be very fatigue specific. I'm going to talk about three main sources of uncertainties. The first one is about the geometry of the monopiles, because we have the transition piece that makes the connection between the pile and the turbine, and usually this piece has a larger diameter than the pile itself, so it can introduce some geometrical variations that will change a bit the loads, especially considering the hypotheses that are done in the design models. Then I will have a brief talk about the nonlinear loads that applied on monopiles, focusing on the high frequency loads that are the most involved in the fatigue, because they correspond to a lot of cycles. And then I will give a brief word about the stretching models that are one of the sources of uncertainty of the loadings on monopiles. So what we are going to discuss today, I didn't know exactly who will participate, so I have some slides of introduction about the theory I will discuss today. So the first thing I will discuss is strip theory. So it's maybe the most used theory when trying to describe the wave loads on monopiles. So the idea is to cut the monopile into segments on which we can compute loads based on the wave kinematics using formula. So probably the most known formula is the Morrison formula. On for monopiles, offshore wind industry, we have this Makamian-Fuchs correction that helps to account for high for short waves loads on monopiles. So basically, what will be applied in this presentation as a strip theory will be a Morrison formula corrected by the Makami-Fuchs method, and we will not consider the drag loads. So we'll have a force that is directly proportional to the acceleration, and this inertia coefficient, Cm, will not be taken as a 2 like we do in the Morrison equation. It's not an empirical parameter anymore. It will be determined analytically to account for the diffraction more precisely in Morrison. And so even with a very simple model like this, with just a force coming from the acceleration on a linear wave field, it's possible to derive second order wave loads. So they are inherent to the design of the models. because this is a time domain integration that we are doing when we design offshore wind turbines. And so we integrate the loads until the instantaneous position of the free surface. And just doing that with everything linear, we are creating second order wave loads. And, one idea will be to compare what is the prediction of those time domain models against more accurate models. So as I didn't know exactly how familiar you are with this idea of second order wave loads, I just taken an example that I found in Bernard Mollen's book, which is very nice actually for second order loads analysis. And so it's explained that if you have just free surface elevation that is regular and linear, so just a cosine function with an amplitude that is half the wave height, the force that will be produced by a model of second order will have a component at the wave frequency in the horizontal force, and also a component at twice this wave frequency. So this is what I will call high frequency loads today. That will be the loads that are produced not in the wave spectrum itself, but are associated to a combination of several wave components that are producing double frequency or at least some frequency loads. And of course, those loads, even if they are smaller, as they are associated to a higher number of cycles, they can produce a contribution to the damage equivalent loads. So this is the first family of models that we will discuss, this sweep theory. And the other one is the potential flow models, for which the wave force are not obtained by associating coefficients to a wave kinematics, but they are computed directly by the pressure integration on a mesh of the monopile in that case. So from the very general problem that we have here on the left of the slide, and I promise it will be the only slide with a lot of equations. After that, I will try to have something more easy to read. But from this very general problem on which we have a description of the wave pressure using the potential on the hydrostatic components, we have a problem that we can solve in the fluid. So the fluid is assumed fully nonlinear. So the free surface is not something very flat like we have on this picture, but we have crest and trough. We have boundary conditions on this moving boundary, and it's possible to solve this problem in a fully nonlinear way, but it's very costly. So what is done in the industry, mostly in the oil and gas industry and for floating wind turbines, is that we try to solve this very general potential flow problem at first order in order to derive forces at the wave frequency. And it's also possible to solve this problem at second order in order to access these nonlinear wave laws that I talked before. And so in order to solve the linear problem, we have a set of equations. So we have the Laplace equation in the fluid domain, some boundary conditions that we can linearize as compared to the very general problem. And so we can derive linear transfer functions. By linear, I mean that they are producing loads in the wave spectrum. And for the second order wave loads, the problem is a bit more complex. We have different sources of linear wave loads. Some come from this velocity square term. Others are coming from the variation of weighted surface, and others are coming from directly the second order wave potential. So we have different terms that we can compute with an equation, a set of equations that is a bit similar to the first order problem, but we have a lot of system of equations to solve because there are a lot of wave components to consider. But this is something that is done in the industry and in various solvers. So it's what we call the quadratic transfer function. It's a way to express the second order wave loads in a synthetic way using transfer functions. And it's something, let's say, quite equivalent as the strip theory that I mentioned before, they are producing forces at twice the wave frequency at some frequency of different wave components. But of course, we can consider these models are a bit more accurate because the diffraction problem is solved in a better way than what is done for the strip theory. So it will be our reference model when we compare the strip theory to our reference. So trying to go more in depth in what is the program of today, I will start by give you the framework of the study with the cases we have investigated, the method and codes we have used, the kind of output I wish to present you in the rest of the presentation. Then I will have 5 slides about the effect of the transition piece on the wave load. Then 5 slides on the comparison between the wave loads predicted by the potential flow on the strip theory model. And then 2 slides about the stretching models on the conclusion. Yeah, so moving to the cases we have investigated. So on the left part of the slide, you have an idea of the scatter diagram that we have used for this study. So it's a HSTP scatter diagram taken from the Teesside farm. It's a farm operated offshore the UK by EDF Renewables. So it was not possible to give you exactly the values. So you just have a plot. Basically, the most common wave conditions are in red and pink, and then you have less typical conditions in orange and yellow and green. So basically, we have a lot of small waves, but on a large range of period. We have HS until 6-7 meters. We will consider this wave for the fatigue study. So this was for the side conditions. In terms of study, we'll first do the study on the effect of the TP geometry on the prediction of wave loads using these Makami-Fuchs corrections. And so for that, we'll use the strip theory and the potential flow approach. And both will be linearized. We'll have only linear components in this study. And the idea is to say we'll represent a pile with a transition piece by a cylinder of variable diameter, so small diameter D1 that will connect the seabed to the TP, and the TP will have a diameter D2, and then over the TP will come back on a diameter D1. So it's basically just 3 cylinders superimposed. So this will be for study 1, and the idea will be to see how this large diameter section influences the wave loads. And then the study 2 will be focused on vertical cylinders for very simple geometries. And we'll have a look to the strip theory and potential flow, but this time we'll use the second order approximation for both the theories, and we will see the impact we see on the damage equivalent load. In terms of methods, maybe it's worth coming back on this Makami and Fuchs method. So this is the first method we have used. So it's just applying the strip theory with airy waves and quite a nice discretization of the pile, just 10 centimeters segments. So here you have on the right an example of a segment. Each segment will be submitted to a vertical horizontal force that will be only proportional to the acceleration. So I recall here we did not consider the drag, and so the force on the small segment is just given by the water density multiplied by inertia coefficient, the section of the monopile, and the acceleration of the fluid, and of course the size of the segment. And we apply this Makami-Fuchs correction that is done usually for a purely vertical cylinder with no diameter variation to a cylinder that has two diameters, and as it is done in several codes for the design of monopiles, we will consider the diameter at the free surface position to compute this inertia coefficient. So the formula proposed by Makami and Fuchs to compute the inertia coefficient is given on the right side of the slide here. And you see it depends on the k multiplied by the radius of the monopile. But here we have several radius, and it is chosen, like it's done in several codes, to use the radius at the free surface position. And so, for those who are not very familiar with this inertia coefficient, CM, basically I have plotted the module of this inertia coefficient just below the formula. What you have to keep in mind is that for long waves, compared to the cylinder, or at least for thin cylinder, if you want to say it like this, we have Cm that is basically equals to 2. This is the Morrison assumption to consider Cm is 2. And after that, this formula make a decrease of the inertia coefficients to values of 1 or even lower than that in order to account for the diffraction effect. So you don't need to understand really this formula. You have the plot of the modulus of the inertia coefficients just below. And so have in mind that for high frequency waves, we have a reduction of the inertia coefficient, so reduction of the loads. And we have applied this Makami and Fuchs correction until the crest position, so in the whole water column and also in the crest, with a time step of 0.1 seconds, leading to a 10 Hz signal, so it's quite nice to analyze the fatigue. In terms of reference, when dealing with the variable diameter cylinders, we'll have a diffraction radiation solver as a reference. So we have used Nemo, which is open source and free software developed by École Centrale de Nantes. That is really easy to use, and I encourage you to make your test. It's a very good tool. So we can just input to Nemo half the monopile mesh. And so Nemo will compute the full wave loads applied on the monopile. So the incident waves and the diffracted waves are computed by the software, and the local pressure on every panel you can see here are computed. And after that, the software makes the integration of the pressures and give the global force. So this will be our reference, because this is a kind of tool that are made to deal with these, let's say, complex geometries, at least less simple. And we compared that with a strict theory. And our base case will be two water depths that are observed at T side, so quite a low water depth with a 12.5 meter, and a larger water depth with 19 meter. And the idea is that when the water depth is low, we have D2 that is crossing the free surface. So we are using the large diameter to compute the inertia coefficient. And when the water depth is high, we have the small diameter that is crossing the free surface. So we are using a small diameter to compute the inertia coefficient. So the idea of the study is to see what is the level of uncertainty that we introduce when doing this hypothesis. Last section for the methods, it's concerning the high frequency load, so the sound frequency that I mentioned before. For that, as we were working with very simple geometries, basically just vertical cylinders, we were able to just use analytical or semi-analytical formula. So for the linear forces, we use this Makami and Fuchs analytical solution that was implemented in Python by Arsène Amoureau at EDF. For the second order wave load, so the QTF, quadratic transfer function, we compute it using a semi-analytical Python script developed by Elie Ronger. For both these tools, we made a validation. So for the linear side, we compare the Makami-Fuchs correction to a formula to Nemo first order solution with good accuracy. And for the second order script, we compare the prediction of the Python with the article by Kim and Yue. So we implemented the method given in their article and compare with their results with a very good agreement, so meaning that these codes are, let's say, validated. Okay, and now I would like to talk about the output I will present. As I said before, the study is very focused on fatigue. So I will present damage equivalent load maps. And you have an example here at the bottom of the slide on the left side. The idea is that for each HSTP that we have in the scatter diagram, we compute time series of the overturning moment due to the waves, and then we compute a damage equivalent load from this time series using rain flow counting. We do that 3 times for 1 hour states. We take the mean value of this damage equivalent load, and we have 1 point of the DL map. And if we do that for all the points of the scatter diagram, we obtain this DEL map. So it's a synthetic way to present where the damage equivalent load is high, where it is low. And what I will mostly focus on is a ratio of DL maps. So usually we want not just to have this DL map, we want to compare 2 models. And so we'll have maps, DL ratio maps, like we have on the right side of the slide here, that are just presenting the ratio between the DL of 2 models. So here I have an example on which we have positive and negative values. So for example here for the red and the pink values, we have values of 10 to 20%, meaning that the model 1 is 20% higher than the model 2 for the HSTP couple that we are considering. And if we have a negative value in green or yellow, it will be the opposite, meaning that the model 1 will be lower than model 2 for this HSTP. But I will come back on every slide on which model is which. Okay. So let's now move to the study 1. So the effect of having a variable diameter on our monopiles. So here we compare the linear string theory to the linear potential flow given by Nemo. We have the relative error on the DL, so the ratio here. And we see that basically we have only positive values, meaning that the string theory is always higher than the linear potential flow, meaning that we find a higher damage equivalent load using the string theory than what we would have in a potential flow method. Meaning that we are conservative using string theory, and we have differences in the order of some percent, with very low variation with HS, which is logical and expected for a linear model. But we have variation depending on the TP, with more differences for large TPs and smaller differences for small TPs. Meaning that probably the kinematics associated with small TPs does not penetrate a lot in the water column. Most of the loads are applied on the large diameter side. On this slide, we make the comparison of 2 values of D2. So on the left side, we have a small ratio D2 over D1. Only 7% additional diameter for D2. On the right, we have 15%, and we see that we have more effect of using a big diameter on the DL, we have DLs in the range of plus 0% to plus 3% for the small value of D2, and we have 2% to 9% effect on the DL when using a large D2 value, meaning that the bigger the diameter, the bigger the effect on the DL. And so here this is quantified, so we can use it. And here we have exactly the same plots, but for a large monopile. So yes, I forgot to mention, but we have two monopiles in this study. The small one is for the T-side, is taken from the T-side farm. So it's a 2 megawatt monopile. And we have a larger monopile associated to a 10 megawatt turbine that we will call the 10 megawatt monopile or the DT monopile. And so what we see is that when we move to a small monopile to a bigger monopile, we have less effect of having this transition piece on the global load, with 1% to 3% effect only on the global DL. Now I move to another water depth, so the 19-meter water depth. In that case, we have the inertia coefficient computed using the small diameter, and we see that this produces the opposite effect as compared to the previous case. So we are predicting smaller loads with the strip theory than with the potential flow theory. So the differences are in the order of 7% for a small diameter of transition piece, to 10 to 15% when we use a bigger transition piece. And so this was for the small monopile, for the 2 megawatt monopile. And if we move to the 10 megawatt monopiles, this effect is a bit reduced. So we have 2 to 6% reduction of the load using the strip theory as compared to potential flow. And moving to the bigger ratio D2 over D1, so bigger transition piece, we have 3 to 10% differences. And still, we have always this very homogeneous response with no influence of the HS on the response. So basically, we see that larger monopiles are maybe less affected by this change in diameter than small monopiles. Now I move to the second study. So it's a study on the high frequency loads, so the sum frequency. And here it was just in order, to explain a bit what I will discuss later. So here we have QTF matrix, so quadratic transfer function matrix, meaning that, for example, if I look to this top left QTF plot, so to the top right, if I combine waves of 3 radians per second on 1 radian per second frequency, I am able, both with the strip theory and with the potential flow method, to determine the amplitude of the force that is produced when I combine these two forces. So if I do that for any couple of frequency, I have this kind of plot of matrix that give me for any couple the level of force that I can expect from the wave field. So the top values here, the top matrix, are associated to the strip theory. And you see they are, let's say, pretty homogeneous with little variations. And here at the bottom of the slide, we have the prediction of the potential flow method, so that is expected to be more accurate. And we see here more variations, in particular for the high frequency. We have very strong oscillations that we do not see with the strip theory. So as it was maybe not that easy to see, I propose here another view with a curve. So on the right part of the slide, we still have our QTF matrices. And what I plot on the left part is the diagonal of these matrices. And so the plane lines are associated to the strip theory. And you see we have some variations and oscillations, but they are of more limited amplitude than the dashed lines results that are taken from the potential flow theory. What we can observe from these curves is that in the typical wave spectrum, so between 3 seconds and 15 seconds, typically 40 side, we have some differences between the strip theory and the potential flow predictions. For long waves, we have quite similar predictions with the same tendency on the imaginary part of the force and almost no real component in the force. Sorry, but for shorter waves associated to a shorter period, so higher pulsations, we see significant differences between the prediction of the strip theory that seems to be higher than the predictions of the potential flow method.
Hi, Christophe. Christophe, sorry, may I interrupt you? Just to remind you, if you may conclude in a few minutes, because we need to be sure to save times for questions and second presentation. Sorry, go ahead.
I'll try to be fast, but I have a couple of slides.
No, sure.
Okay. So we have some differences, and we'll see if we see them in the DL predictions. And so if we apply these two methods to the small monopile, so the 2 megawatt monopiles, we see that for short waves, so for typically TP between 3 and 10 seconds, we have an overestimation of approximately 20% by the strip theory as compared to the potential flow. And when we move to longer waves, we have almost no differences between the two methods. And what we see also on this graph, as compared to the graph before, is that we have a variation of the DEL, both with the TP and with the HS, because now the problem is non-linear, so we can expect to have different behavior for large HS and small HS. Okay, so I'll try to be short. So here it's a comparison between 2 diameters of monopiles, and we see that we have pretty the same behavior. We still the strip theory producing higher DL for short waves and large waves, and almost no differences for the long period. And it seems that the difference between the models is a bit more pronounced for larger diameters. Okay. And if we move now to a modification of the water depth, we have still on the left part here the prediction for the small monopile in 12 meter water depth, and on the right side in 19 meter water depth. And we see that we have less effect of less differences, at least between the strip theory and the potential flow method for the large water depths as compared to the small water depths. So basically, it seems like the most critical cases are for low water depths and for small monopiles, thin monopiles. But still, we have the same tendency with 15 to 20% difference. Now I have 2 slides on the stretching models. So for those who are not familiar with the stretching models, it's a way to compute the kinematics in the wave crest, in particular for irregular systates. It's quite important to avoid overshooting the kinematics. So basically the idea is that if the linear theory is predicting the orange curve here, in reality, what we would observe at field would be something a bit less, a bit lower than this kinematics. So this is noted real velocity profile in blue here, and we'll have a bigger and bigger difference when we go to the crest of the wave. Even if we have something quite correct in the water column, when going to the crest in general, if we do not correct the kinematics by a stretching model, we will have 2 big accelerations and 2 big loads. So there are plenty of stretching models that have been developed in the literature. For now, what was presented was using the vertical stretching models, meaning that we follow the linear theory, and when we go in the crest, we consider that the kinematics in the crest are the same as the kinematics at the mean surface level. But it is not the most common stretching model. We have other stretching models that are most used in the code, the Wheeler stretching, the Wheeler plus stretching. So the idea of these models is to try to avoid this overshoot in the kinematics by changing a bit the vertical scaling. So for the linear theory, when we reach the mean sea level, we have a ratio here that is 1, meaning that the kinematics is given just by the amplitude of the waves and the wavelengths and the wave period. And when we go in the crest, we'll have some overshoot. And the stretching models are a way to change the reference for which we obtain 1. So for the Wheeler stretching, we obtain 1 for the instantaneous position of the free surface instead of for the mean position. And for Wheeler plus, we make small overshooting, but not a very big overshooting. So it's a way to try to capture better the kinematics. And so moving to the results, we observe here that the stretching models have kind of the same features as what we have seen for the nonlinear wave loads. So mostly an effect on the small period, and less differences for the high period, and mostly an effect for the large waves, and no effect for the small waves. And it seems like the Wheeler plus and the Wheeler stretching are producing a lower DL than the vertical stretching, which was pretty expected because they are reducing the kinematics, so they are reducing the loads. And the typical order of magnitude is between 0% here to, let's say, 15% for the shortest and biggest waves. So quite similar to what we have seen before. So I move now to the conclusion. So for my conclusion, I will talk about global DEL. So for now, we had a DL maps with this quantity plotted for any HSTP couple. When I talk about DL map, I multiply the DL by the probability of occurrence of HS and TP, and so I obtain a global increase or decrease of the fatigue damage. So what we have seen is that for the TP, the variation of geometry of the monopiles due to the transition piece, the strip theory varies from -7% to +2% with respect to the potential flow. So globally, we have a tendency to underestimate a bit the loads in most of the cases. Regarding the second order wave load, so the high frequency wave load, it seems like the strip theory is producing a higher damage equivalent load on a large range of wave periods. So this leads to approximately 8% of additional damage equivalent load for the case we have seen here. So on the T side farm, so it's for sure side dependent, but on our case it was 8%. And when we move to a small pile diameter to a larger pile diameter, we move to 8 to 10% difference. So it seems like the bigger the monopile, the bigger the difference, which is quite intuitive again, because we have more and more diffraction effect when we move to larger pile diameter. But here it's quantified for the project. In terms of limitations, just 1 minute. I have to say that the comparison is a bit unfair when we compare the potential flow on the strip theory, because for the second order wave loads, the potential flow model considers that we have second order incoming waves. So we have second order free surface elevation that is not accounted for in the strip theory model. So this is a study we could do. It's not easy to imagine how we can interface Makami Fuchs direction with a second order wave field, but this is something we could work on. I recall here that we have considered the structure is fully rigid, so we are talking about hydrodynamic loads in terms of DEL, so it's not a load in terms of structural response. So we are just quantifying the loads applied on the monopile. So it could be interesting to investigate flexible monopiles in order to see how some frequencies are magnified, and how it changes the conclusion we had on the DDL. And I remind you that we didn't consider the drag loads here because drag loads are the same for the two kinds of models, so we wanted really to focus on the differences. And probably if we integrate drag loads, we will reduce a bit the differences we had in the DL because we'll add a common contribution to the two models. So sorry, Martin, for being that long.
No problem for me. Thank you, Christophe, because it's an important result of the Hiperwind project, and you clearly shown some significant change, I will say significant approximations that are introduced by the strip theory of MCF, including some non-conservative one. So I think this may be of interest for the people who are connected and people that are working on design specifically. Anyway, we may like time for I will say we have of course time for few questions, but we may lack time for a lot of. So we try to take some questions now, and then if there is no time enough, I invite the people to don't hesitate to put them on the chat in order for us to address the question later, if we don't have time to answer all of them, to take all of them. But of course, please don't hesitate. If you have any questions at time, you can raise your hand, and in order for us to give you the floor. Okay. So if there is no question that is raised now, let me say that yes, I can see there is an hand. Sorry, Cyril Bourgoin. So
yeah,
I give you the floor. Yeah, sorry.
Thank you very much for these presentations. Very interesting. Just to be sure to understand the comparison.
Could you first? Sorry, but could you first introduce briefly, meaning your organization?
Yeah, sorry. So Cyril Bourgoin from Windglass, working in load simulations for offshore wind turbines and floating offshore wind turbines. So daily users of simulation tools such as Bladed, OrcaFlex, or Deep Line Swings. So really interested in those kind of topics for sure. So thank you again for these presentations. I may have one question regarding the way the hydrodynamic database, or the way you are considering the periods for the hydrodynamic database. Could you just give us an idea of the lowest period that you have used or consider when you calculate the loads from the diffraction radiations contributions? How low did you go when you have done your NEMO calculations in terms of periods?
Yes. I went until 0.05 radians per second. It would consider to be 120 seconds as a period. So very low.
Okay. So that is indeed including some load calculations for very low periods. Okay, thank you.
Yes.
Okay, thank you. So time for one question more, if you want. I'm just checking if I'm missing a raised hand, but I don't see one. Okay, so if you mind, once again, you are pleased to write your question if you think to another question during the second presentation, and I'm just giving the floor directly to Adria and Fabien, who are going to give you a talk on the floating case study of Hiperwind and focusing on the drag coefficient uncertainty. So please go on, guys.
Okay. Thank you very much, Martin. So I will share my screen. I guess it's okay. Yeah, do you see my screen? Yeah,
it is okay.
Okay.
Yes.
So yeah, hi everybody. So my name is Adrià Borras Nadal, and I will make this presentation with Fabien Roubaud. So yeah, so let's see if okay. So the table of content. So the agenda it's obviously to introduce a bit the topic and the objectives, but also explain you the models and the methodology that we have applied in this study, and all the validation cases that we have performed also, and the validation cases before going to the full floater case. We will explain that during the presentation, and conclude and see the ongoing work and what we would like to continue to study in this project. But yeah, before seeing all those details, maybe it's important to introduce the topic. So the Hyperwind project, you know already, Martin presented at the beginning of the webinar. So we have performed this work on this project. So it's H 2020 Research and Innovation Program project. The partners, and yeah, so this introduction, maybe we can keep it. It's only interesting to see a bit the academic partners and the research organizations. Also, I think this slide, it's nice to see also the competencies and what we have performed in this study, EDF and IFPEN. So we see here the load simulations and the hydrodynamic loading. So we are in this topic. Again, we have this organization of work packages. So we are here, as Christophe presented before, so the farm and turbine load modelings work package. Yeah, maybe to focus on today on this work package 3, we had a lot of topics to deal with, but the focus of today, as we said before, is the 3.2. So and more specific, this orange line here with floating. So the main difference is the main particularity of the topic is that it was really focused on floating problematic. So yeah. So what about hydrodynamics in boat design? So I think it's always important to introduce a bit the topic and remind maybe some key elements of seakeeping. I think it's really interesting to see a bit this introduction, this slide, because it's important to be aware that the state of the art, it's directly coming from oil and gas industry methodologies. So what we find, if we want to apply it to float, I think it's interesting to see that the people of floating wind turbine industry for the moment is still really focused on those methods, and those methods are based on main two theories: the potential flow theory applied for the so-called large bodies. So what we mean by large bodies, we mean that we're gonna take the modeling of the diffraction effects when the body will be really important compared to the amplitude of the wave, the incoming wave. And here the flow separation effect will not be so dominant, but the second aspect, if this flow separation effect is more important, so the current methods will use the Morrison empirical formula. So Christophe introduced a bit this formula before. So we can consider this small body theory as an empirical one, where we will define the loads of the forces that we have to express in two terms. A drag dominant term with a drag coefficient to fit, and an inertia dominant term. So I think what's interesting here is to see that that's directly coming from oil and gas, but it's really important to ask ourselves to see if for marine renewable energy that's convenient or not. I think we're all aware that we have more economic constraints and less safety constraints, and we really want to design a bit better our floating structures that maybe the past oil and gas topic. So it's really important, I think, to see a bit the methodologies and to ask ourselves about the current limitations. So of course we can ask ourselves about the validity of or accuracy of the tables that people are used to use when we have to fix those coefficients, because we are in an empirical formula, so those coefficients have to be determined. And also considering different motion periods, also different waves, different platform size. I think it's really different on this new topic. The platforms can be really different, and well, it's interesting to ask a bit about the methodologies that we have used during those 30 years or something like that. So another way to see that it's, as I said before, is that those classical methodologies are mainly focused on linear potential flow model. If you want to take the viscous effects of flow separation into account, then we use this formula of Morrison formula that I presented. And well, I think we can maybe see if those tuned coefficients are still valid when working on FOAT. And well, so the main question here is how CFD can help to determine hydrodynamic coefficients for floating wind turbines, and that's the focus of the presentation of today that we will present with Fabien. So it's really 100% CFD focused. And let's talk now about models and methodologies. Well, so here during this project we have performed numerical wave tank simulations. So we talk about CFD numerical wave tanks and see how they can help to calibrate empirical coefficients for engineering tools, of course. So those aeroservo hydroelastic tools that we talked before. And for that we have performed two type of conditions. So fixed body in wave conditions, as you can see here on the left. In this case, the body is fixed even if it's a floating one and it can move. In this case, we have fixed it to study properly the incident wave coming. And we have also performed some forced oscillation in calm water. So here it's an example of pitch one, but we have performed more than. So that those two kind of simulations have performed on different tools. We will see that later. Just before, an important also an important point it's that the main focus of the study is to study the U main floater. So as seen here in the picture. But to validate our approach and the project, we wanted to make a step-by-step methodology, and that's why we have split it in three different cases. So the first one is focused on the pontoon here in 2D, also to be more simple and to increase the complexity. So then we have also studied separately a case of cylinder piercing the surface, and at the end we have made the comparison between the both codes in the full floater, because at this stage we did not have some experimental data on the full floater. So that's why it was interesting also for us to separate the problem and to be able to compare our methodology with the experiments. So well, just before let Fabien introduce the rest of the presentation. A few words about the tools. So we have used two different tools. So Fabien has used Neptune CFD developed by EDF. And on the IFPN side, I have used OpenFOAM. So yeah, here you have a short description of both codes. I think we run quite out of time, so maybe we cannot detail too much. But just to say that the tools are quite similar concerning the wave generation methodology. On our case in AFPen, we have with OpenFOAM we have used the wave2foam libraries, but well, I think maybe Fabien will detail a bit more on the Neptune CFD particularities, but of course on OpenFOAM it's quite a classic one because it's a really used open source toolbox with a WOF system and mules to track the free surface. To mesh, we have used the snappy hex mesh to feed the body. So yes, and when we have made the oscillation, the imposed motions, we have used the mesh morphing approach. But yeah, for Neptune CFD, it's another approach. Yeah, maybe Fabien, you can take over and introduce Neptune CFD before explaining the rest.
Yes, yeah. Thanks a lot, Adria. It's true that Neptune CFD and OpenFOAM are really close from one another, mostly because they are both finite volume approaches. But when OpenFOAM uses a volume of fluid approach, which means only one velocity field that is ponderated by the mass density, in the Neptune CFD approach, you have two different velocity fields, one specifically for the air and one specifically for the water, which allows us to have a jump in terms of velocity at the interface, and the algorithm to sharpen the free surface is easier to maintain and to compute. And the other difference is that when OpenFOAM fits the mesh to the surface, so you have a boundary at the position of the body. In Neptune CFD, we use a variable porosity method, which means that we have a discrete forcing that represents the mesh as the object, meaning that the mesh is fixed even though the object is moving, which simplifies a lot the meshing, and especially in dynamic cases.
Yeah. Okay.
So if we continue to the extraction of the hydrodynamic coefficient, the question is, once we have a CFD simulation, we obtain a discretized time series of the load, for example, there fx. And the question is how to represent it with only two coefficients, CD and CM, given that we have the velocity acceleration from a potential model, for example, or from a nonlinear model that doesn't take into account the body. For that, there is multiple methods that I will present in the next slide. But just on this slide, what's important is that you reduce the complexity of your problem from a time series to only two parameters. And by doing so, you introduce hypothesis, of course, because you lose a lot of degree of freedom. And the main hypothesis is the Morrison hypothesis, which means that the body dimension should be very small compared to the wave dimension, and that's it basically. And also that's why this hypothesis comes from the fact that the body should not have a large influence on the wave kinematics.
Yeah.
So on the top of this slide, you have a reminder of the previous one, and you can see that there is many methods to obtain those two coefficients. The first one is to try to minimize the error by comparing the time series to the reconstruction. So you have two variables that you can change to minimize this error, this L2 error, E. And you can see in more detail either in the reports that you can find on the Hiperwind website or in the article of Venugopal, the equations to obtain CM and CD from the from this method.
Yeah, we perform also on IFPN side. We perform also that during a PhD study, and it was similar to Venugopal. So yeah.
And the other method is a method that is an extension from a method coming from Array, which is a relatively old method. Basically, it comes from the fact that within the CFZ load, you have a nonlinear part, meaning that it's not just a sinus, but it's a sinus plus something of higher order. And in theory, when you impose a movement U as a cosine, you will have, in the expression of the model of the Morrison model, a part that is nonlinear due to the UX times absolute value of UX. If you do the limited development of that, you will have a small terms in 3 omega, of frequency 3 omega. And you can compare what you obtain when you do the Fourier transform of the CFD load, and compare that to the values that you have in the 3 omega part. And in that case, you can deduce what the CD is by looking just at the amplitude of the third order load that you obtain. The great thing about this method is that it doesn't rely on any phasing between the load and the kinematics. But the drawbacks is that it's based on a very small amplitude, like 16% of the total magnitude, something like that, and it's only valid for imposed motion. Why it is only valid for imposed motion? It's because you have to impose a linear motion and get the non-linear part of the effort. If at the beginning you impose non-linear kinematics, for example, when you give wave to the model, you will have a non-linear part. So at the end, the non-linear part of the effort will both be the non-linear part due to the fact that there is non-linearity in the load, but also coming from the non-linearity of the wave itself. And it's difficult to identify which one is which one, basically. So the first case, as Andrea said, is a simple 2D rectangular cylinder that represents the pontoon. Note that this pontoon is made at the scale of the humane floater, so which is not exactly the same as the scale of the Venugopal case, but it's really, really close. For example, in the Venugopal study, the aspect ratio is exactly 0.5. In our study, it's 0.56.
Yeah.
We have tested 4 different waves, so that we get a representation of the CD with respect to the value of Kc.
Yeah.
On this slide, you can see the mesh that we used in both studies. So on the right, the classical open foam mesh that you can see that the mesh is fitted to the cylinder. We have a refinement zone close to the cylinder, close to the wall, and also at the free surface. And on the left, you have the same types of refinements close to the body, at the free surface as well. And you can see that in black is shown the porosity field that represents the object. So it's easier to mesh, but you have to treat the porosity in the development. And here are the slides showing the results compared to the Venugopal results that he obtained experimentally in 2002. On the top, you can see the inertia coefficient, and on the bottom, the drag coefficient. On the left, it's for the horizontal axis, and on the right, for the vertical axis. We have a different simulation in this slide. Mostly, we have 2 simulations for Neptune CFD with 2 different turbulence model. The first one is a K epsilon with a slight tweak in the projection. And the second one is a REG model, which is roughly second order, so should be a bit more precise, but is also more expensive to compute. And if you do not respect the criteria in terms of cell size, you may have some surprises. At the end, what we obtain is the OpenFOAM, if I remember correctly, used a K omega SST stabilized model from Larsen and Furman. So what you can see is that in both CM and CD, we have good agreement between OpenFOAM and Neptune CFD with both turbulence model. We have small differences for large chassis with the REG model, and that is expected to be originated from the two-course mesh that we used in this simulation.
Okay, I don't know if it's okay for you, Fabien.
Yeah, it's okay for me.
So that was an important step for us, because we could be able to compare the coefficients directly with experiments. So, but we were in 2D. So then the next step was to continue the methodology and to deal with a 3D case. So that's why we have selected another case of literature before going directly to the full floater case. Here the objective was to make the 3D comparisons of loading efforts on this constrained surface piercing cylinder. So here the experiments are based on the Stansberg of 97. But those experiments are quite used also in the literature, because they were intensively used in the OC5 project of Amy Robertson, and in the framework of IEA Wind. So here we have selected 3 different waves from this test campaign. And the time series of efforts have been compared to the experiments and analyzed and compared between both codes. So here you can see the 3 waves that we have selected, and with different range of cases. So yeah, here it's an overview of the simulation. That's exactly a simulation performed during the PhD. I think this video was not made for myself. It was made from Constance Clément, that I can thank, because we have made a lot of work that we have used during Hyperwind project during the PhD of Constance. But here we have selected different waves from the PhD. Here we have directly the results. So the 3 graphs that you see are the horizontal wave loads on the rectangular. The rectangular cylinder. Yeah, it's quite up. It's the cylinder. It was for the before.
Maybe confusing.
Here, yeah. No. So here it's the piercing cylinder. So here we are looking at the horizontal wave loads of 3 different loads. So the blue curve, it's called NREL. It means the experimental one. The orange one, it's the simulation made by IFPEN with OpenFOAM, and the other with solid lines are different tests of Neptune CFD. So I think here what's important to see is that, of course, we have a good agreement between OpenFOAM and Neptune CFD, but also with experimental results. So what's also interesting to see, it's maybe in the 3rd wave we had a little bump that we encountered when with the incident wave that we have catched quite well, and we have seen that depending on the mesh refinement we were able to catch the bump. But yeah, I think here the results were quite encouraging for the next step. So the next step is the full floater. Maybe Fabien, you can go on.
Yes, thanks, Adria. So because the goal is to get the CT and CM on the full floater, because it's what is used in the engineering, mostly during the design part, we define different zones of the floater, and we choose CD and CM for those different zones. What we are going to do is exactly the same thing: define different zones and try to fit a CD and a CM on those zones. For that, we have studied 3 different benchmark cases. The first one is an incident wave of period 10 seconds and wave 8, 6 meters. The second one is a forced sway motion. So we impose the body to move along the y-axis in a period of 10 seconds and amplitude 3 meters. The goal is to get roughly the same cases in all the cases. And the last one is a forced heave motion, so vertical displacement. Of course, loads won't be the same in the different zones. For example, on zone 4 and zone 5, the load will be almost null in a sway motion, but will be relatively important in heave motion. So the first one I'm going to show you is the sway motion, so movement along the y-axis. And we can see here the time series of the load along the y-axis on the zone 2. So you can see on the upper figure on the right where the zone 2 is located. It's on the center cylinder. So on the left, you can see the comparison between NCFD and OpenFOAM, and you can see that both of them are relatively close. We have a small high frequency problems with NCFD, but it's only due to post-processing problems when we extract the load. There is no physical implication on the simulation itself. And on the right, you can see a reconstruction of NCFD with the method L2. If you remember correctly, I spoke about 2 methods of extracting the coefficient. The L2 method was to minimize an error L2. And I said that it was very sensitive to a phase shift. And you can see that between NCFD and OpenFOAM, we do have a small phase shift between the two loads. And you can see on the table on the bottom that the L2 method on the CD yield a factor of 3 between OpenFOAM and Neptune CFD, 1.07 for OpenFOAM and 3.07 with Neptune CFD, which is a large discrepancy, even though with the O3M method, so the order 3 method, we have very close results between OpenFOAM and Neptune, and the CM itself, which is the main component of the load. The inertia part is dominant in that case. We do have very close results between OpenFOAM and Neptune CFD with both methods. So the conclusion here is on this slide is that given on the method, even if we have very close time series, the phase and a small phase shift can have a large impact on the obtained drag coefficients. So for the
please also okay. Same problem.
We're going to accelerate.
Just try to conclude because you have 2 questions already in the chat, so that's why just to let the time for questions.
So we cannot skip. We cannot skip the video. No, I'm joking.
So there is a vertical motion imposed on this one, and we compare on zone 3. We basically have the same results. We have very close time series between Neptune and OpenFOAM, but the reconstruction might not be completely satisfactory, and it's assumed that it is due to the Morrison hypothesis that the body should be small compared to the movement, and that it was derived for 2D effects. We tried to apply it in a completely 3D case, and we think that it's not impossible to completely say that the 3D effects are negligible in this complex 3D case.
Yeah.
So I'm going to, I think, pass this slide because it's basically the same conclusion. And the last benchmark case is an incident regular wave on the full floater, and we have a video as well that we can't pass.
No, that's the result of all the work.
So yeah. So this is so on this case, if you remember correctly, we cannot use the O3 method because we have nonlinearity that is contained in the incident wave. So we only compare the L2 method there. And we can see that even though we, again, have a very good agreement between IFPN and NCFD, we do have the drag coefficients that can be quite different for the different zones that we consider. And note that the Nemo case, which is in green there, cannot represent any drag effect because it's in the theory of the first order potential flow. So the drag effect is contained between in the phase shift between the Nemo curve and the, for example, NCFD curve. So even though the phase shift is very small, this small phase shift contains all the CD, which means that we once again have a large sensitivity of the CD to any kind of small errors that we could have in the simulation.
Yeah.
So I'm going to let Adria conclude.
Yeah, sorry, it's a bit fast, but maybe we can take one or two questions. But I think, yeah, to conclude, I think we have seen an agreement between the time series on the loads between two CFD codes. We have made this step-by-step methodology with simple geometries where we have seen that the CD is correctly gauged, so that's a good thing. But we also see that Morrison model does not also always correctly fit the obtained time series. So as Fabien said, we have identified two main reasons. So the CD determination is very sensitive to the phase shift with the classical, I would say, classical method of least square error, and yeah, the 3D and diffraction effect cannot be accounted for. So that's also a Morrison formulation limitation. So then I think an interesting point was also this extension of a method that Fabien has developed during the study of extraction of coefficient that can be used for forced motion. And yeah, so we can recall also that the drag contribution is small before the added mass contribution. So I think it's also interesting to remind that the report has more information.
Sorry, maybe I will interrupt you because
no problem. So yeah,
and people can read. You can put the slide before if you want. We had times, but not so long. So I apologize for the extra long time, including mine at the beginning. So first, if I think in the order, there is Amin Gadirian. If you want to present yourself, which session are you? And you had a question about the extracting method of the coefficient in slide 20.
Hello. Can you hear me?
Yeah. Yes.
Yeah. I am Amin Gadirian. I am a senior engineer, load engineer at Stistal Offshore. We are developers and designers of floating foundations for wind turbines, offshore wind turbines. And I have written already my question. I was a bit unsure about if you have already presented the extraction method of the coefficients in slide 20.
Yes, in slide 20, if I remember correctly, it's the Venugopal experiment. And because it's under incident wave, we use the L2 method because the other methods that I've presented to extract the coefficient cannot be used in case of incident wave. So the answer is that we use the L2 method in there, and this L2 method comes from the paper of Venugopal action.
Yeah, and here the only difference that can reach it was really the least square method that we have written on IFPN side or EDF side. When of course we can have slight differences, but we see that it's really close on this purple against the red method.
Do you also know what is happening in the? Oh yeah, sorry.
Yeah. No, please.
What's happening in KC 1.75 with the? I think the
green one.
NCFD case.
Yes,
the green point.
This point is obviously wrong, and it's probably due to the fact that the turbulence model is too high order, considering the coarse discretization that we used in the mesh.
Yeah. Okay. Thank you. Thank you for the presentation.
Okay. Then we have a question from Guillaume Vinet from IFP Énergie Nouvelle. Guillaume, I don't know if you are still connected.
I am still, and I can be quick.
Yeah, thanks.
So yes, just to tell you that I was involved in this kind of stuff a few years before with Adria, but I'm still interested. And I have a question, yes, maybe about for you, Fabien, about Neptune. Do you need to refine a bit more since you don't have the same strategy to take into account the solid? So I'm wondering if you need to refine more compared to OpenFOAM to get the same accuracy at the end.
Actually, I do need to refine more, but not because of the different strategy for the solid, but because of the different strategy for the velocity.
Okay.
There is less model to represent the free surface. So when we use a multi-fluid approach, we usually need to find a mesh at the free surface interface. For the solid parts, it's less true from what I remember as well.
Okay, thank you.
Thanks for your question.
Okay, thanks, Guillaume. And we have a question also maybe of Guillaume Damblanc that has raised his hand.
Yes, thank you, Christophe. First, thank you very much for your presentation. Yes, I have just a question. So I'm France Énergie Marine, if I have to introduce myself. Yeah. And I work mainly on the free structure interaction topics. And just perhaps in terms of methodology, I'm wondering if you compare both CM extraction, because you perform both captive test on one side and forced oscillation also. But for me, in captive test, you will get the inertia coefficient, meaning related to the wave excitation. But in the other case, you will catch the added mass coefficient, which is related to the radiation. And it's quite different. So I'm wondering if you compare both, because I performed such work on other topics for oil and gas before, and the main conclusion was that the relation between the inertia coefficient and added mass coefficient was not still valid as for cylinder, because you have the relationship CM equals CA plus 1, and but this is valid only for slender cylinder, and here we are far from a slender cylinder. So I'm wondering just if you intend to use this CM coefficient in both cases. I don't take clear, because if you perform some comparison with the body moving in waves. I'm not sure if my question is clear or not, but
yeah, but the thing is that here we don't have made the motions of the body.
Okay.
So, but yeah, that's clearly a topic of interest. But
Yes.
but in our case, to avoid a bit this kind of interesting topic that you are mentioning, we have focused on fixed body.
Okay.
Yeah, so in fact that's why it was, maybe we were not clear enough, but we have only performed I think this slide at the beginning. Yeah,
only captive test.
Yeah, it was imposed oscillation motion and incoming waves without motion, but
not both.
No. But of course it's an interesting topic, and I don't know if there is some research solutions available. I think OC7 project will deal with that later. But yeah, interesting question, but I don't have the answer.
Okay, thank you.
So thanks to Anne on this interesting outcome that could, of course, be the topic of future research, definitely.
Yes, for sure.
And so it's time to conclude because we are 6 minutes.